Right, thanks for coming. So this week we have Jang Soo Kim, who is professor at Sungkyunkwan University. And we talk about something about the initial title was like semigroup of functions.
Oh yeah,
but
I
anyway.
noticed that it's actually a monoid.
Okay.
Yeah.
So we talk about long distance, right?
Okay, yeah, thank you.
Please.
Thank you for the invitation. And when I first scheduled my talk, I didn't realize that there will be a winter school, and I'm really feel great that it's a winter school with so many people here. And I actually doing mostly enumeration and algebraic combinatorics, but I recently had some project with Yasuhide Numata from Sapporo University, and we discovered something that has something to do with what graph theorists might be interested. It's a Slater indices. So I'm gonna tell you the story. So let me begin with motivation. So Sn is the group of permutation. Bracket n means just the set of integer 1 up to n. So permutation is basically a bijection. So group, so we have to have operation. This is just so as a set, it's just set of all bijections, and we define the group operation to be just function composition. And if you compose two functions, bijections is also bijections is closed, and it is a group. And let S sub I to be the simple transposition in Sn. This means it sends I to I plus 1 to I, and then it sends the others just to themselves. And this is called the simple transposition. And Sn, a well-known fact is that Sn is generated by the simple transposition. These are called simple transposition. S1, Sn minus 1. And let me give you an example. N equals 4. So it's not that one. So let's consider f equals S1, S3, S2. So this is a function composition, so we have to read from this way. So this function as a full function, it will send 1 to 1 because it doesn't do anything. The 1 to 1 and 1 to 2. So it will send 1 to 2, and then so f1 equals 1. f2 it will get sent to 3, and then 4, and then just 4. f3 it will get sent to 3 itself, and then 4, and that's it. Oh,
F1 is 2, right?
yeah. Let me see. Yeah, 2. So, this is 1. And F4, 4 gets sent to 3. Okay. And we're gonna instead of just looking at each integer about one by one, I'm gonna draw this as a diagram. This is a 1, 2, 3, 4. Maybe some space here. So S1 will be this. So S1 exchanges 1 and 2. So I'm gonna make this cross, and then just they go like this. And next S1, S3 like this, and S2 is like this.
Do you go from bottom to top?
Yeah, that's a good question. Let me tell you. The convention is, so I'm gonna write down 1, 2, 3, 4 at the beginning, and I'll just write down the numbers as I follow. So this is 2, 1, 3, 4. That's 2, 1, 4, 3. 2, 4, 1, 3. So this is actually 2, 4, 1, 3. Exactly like that. So the way we read is. By the way, I'm gonna from now on identify this with this word 2, 4, 1, 3, which means 1 goes to 2, 2 goes to 4, etc. And this can be read by following this diagram. And this is called a wiring diagram. And if you haven't seen this, but the truth is you have seen this. Because everyone knows this ladder game where when you decide who's gonna buy the lunch today or dinner, you put arrows like this, and then okay, so 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, like that. So this is exactly the same thing as this. Only the difference is I replaced the ladder by just a.
How is this related to who buys lunch? I don't understand.
Or, what?
How is this related to who buys lunch? I don't understand.
Yeah, of course, always Sangil buys lunch.
So one is fixed? Or?
One
Okay, this is lunch. Anyway, okay, now, because we know that any function, any bijection can be written as just a product of the simple transposition. One natural question is, so let W be a function or a bijection or a permutation. Then an expression, we can express W as a product of SI1 SIK. Okay, but obviously there are infinitely many ways to do this. So expression is reduced if K is minimum. If you find the minimum number of generate simple transpositions to express W, then we call it a reduced expression. And in this case, the length of W is defined to be the minimum K. If this is a reduced expression, the length will be K. So in other words, it's the minimum number of simple transpositions you need to write down the permutation. And actually, you can read off this length of a permutation using the wiring diagram. It is basically the number of crossings if the expression is reduced, because X just corresponds to one simple transposition. So if you have a reduced expression, then the length is just the number of crossings. All you need to do is to count the number of crossings. And for it's basically number of crossings in a wiring diagram of a reduced expression. Okay. And a longest word, as the name suggests, our longest element is just an element W with maximum length. So all permutations, the permutations, they have different length. We find a permutation that has the maximum possible length. And for a permutation case, it's quite easy. For Sn, actually there's a unique longest element, namely W n minus 1 dot 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 1. If you reverse this identity, then it's going to be the longest element actually. So for example, n equals 4, so 1, 2, 3, 4. So we want to connect them so that we have minimum possible number of crossings here. But you really have to have many like that. In this case, 1, 2, 3, 4, 5, 6. So 6. And you can actually say that in this case, the longest element has length n choose 2 for this. Because if any two pair, they have to intersect. So for a permutation case, it's very easy, and only one longest element. And this Sn is also called a Coxeter group of type An, or An minus 1. And there are many generalizations, and they have all nice properties. And Yasuhide Numata and I considered to generalize this in a naive way. So a natural question, or at least for us, so permutation is a bijection. Why don't we just consider all functions? So the motivation, let's say fn to be the all set of all functions. No, not necessarily bijection. All functions. Okay, you can still compose functions. By the way, it's not a group anymore. You can compose, but the operation is still there. Binary operation. It is associative. So this is called a semigroup, which was the original title of my talk. But I realized, I searched the Wikipedia and realized that semigroup means just a group with an operator, binary operator, with that is associative. Binary operator. And semigroup is the biggest one. And monoid is semigroup with identity. We have identity because identity map is just identity. So it's a monoid. It's also a semigroup, so my previous title is also correct. And this is group. Group means plus inverse. Every element must have an inverse. So we are here. For permutation case, we are here, and now we are in a monoid case. So, but we have to decide what the generators are. So we will use the same simple transpositions, and we need more generators, obviously. Okay, how can I? Oh, yeah, I think it's okay.
Or you can put all the way down the.
And how can I? Oh, I see. That's good. Right. So we're gonna use one more generator. Let T be a function from n to n that sends 1 and 2 to just 1, and the other to identity. Okay, it's 1, 2. And it turns out that this, if you include this, then together with simple transpositions, they generate this function, the fn. So again, Si behaves like, again, we have this string, ith string, or the ith column, I plus first column, it goes like that. So if the number was attached to this string was AB, then this will interchange AB to BA. And T, for the other hand, T behaves like, maybe right over here. So I column, I plus first column. Oh, sorry, actually it has to be the first and the two.
Right?
And let me draw in this way. This is my convention. So if the numbers attached to these strings were A and B, then this becomes A and A. This will be A. You can check this easily. Then that's so. For example, this is the example that I drew. So in this case, let's see. Maybe I can work with this example. Here, my function f is just this. S1, S2, T, S3, S2, S1, T. This can be identified with this 4, 4, 2, 1, meaning that 1 goes to 2, 2 goes to 4, 3 goes to 2 goes to 4, 3 goes to 2, 4 goes to 1. Okay, and that can be understood using this wiring diagram. So this is a crossing, and this I'm going to call this merging. So they merge. These are two different strings or strings with different labels, but they have the same label after that. So it's the object that we are considering. And we have generators. It's not a group, but we can still talk about the length or reduced expression. So definition for an element in our Fn, L of this is defined exactly the same way. Minimum number of way to express sigma is, let me write this, where AI are basically S1 dot 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 Si minus n minus 1 comma t. Using these generators, we want to find the minimum number of generators needed to express this. This is the same definition, only we had added one more generator. Okay. And again, we're going to define longest element in sigma in F is, of course, an element with maximum largest length. And okay, and another observation here, the length is really the number of mergings and number of crossings. Number of merging, that looks like this K shape, and this looks like a X shape. Of course, we assume that it's reduced. So for instance, here, this is actually reduced. The length is this 1, 2, 3, 4. But that's because you know, this represents this generator. X represents the simple transpositions. So it's really just from the definition. Okay. All right. Now let me give you some examples. Oh yeah, main question. Yeah, main question. The main question. So what is Fn? Fn is the maximum or the length of the longest. What is the length of the longest element? Okay, for the permutation case, we know this is n choose 2. And yeah, it's looks like a naive question, but we discovered that it's quite hard. we couldn't solve. Yeah.
Is the longest one unique?
Yeah, good question. Suggests that there might be more. Yeah, I'll show you. Example. N equals 2. So there are 4 functions from 2 to 2. Let me list them all so that we are all in the following. So in this case, what is the length of this?
0.
Very good. 0. And
1.
this, because you know you have right. I think I need more space. So I want to connect 1, 2 to 2, 1. So we can do that. So its length is 1. The length of this is 0 and 1. Okay. Here we start from 1, 2, and then we want to end up at 1, 1.
One more.
Oh, actually 1 is enough. This is 1 more. This is 1. 2, 2. 1, 2. So if you merge, there is no chance. So we have to first cross. So it's 2, 1, and then if you merge, 2, 2. So the length is 2. So in this case, what is the longest element? So this is the longest element. There's a unique longest element. The length is 2. Good. N equals 3, then there are 3 times 3, 9. There are too many. So
I'm slightly confused.
Yeah?
So over here, yeah, I mean the thing that I'm confused is the order of product. And
yeah, right.
Yeah. So for instance, the last one.
Last one. Yeah, this is S1. So S1T. So this is S1T. So we have to read this way.
Right.
So 1 goes to 2.
So if 1 comes in,
Oh.
then then T gives you 1, and then S1 gives you 2, right?
I think you're right. Maybe I.
And 2 comes in, then 1 So
this looks right.
this is correct.
Yes.
Yeah.
This is correct.
Wait,
but-
wait. Is this
So if you
This-
reverse, right? S1.
right? Yeah. Maybe I.
Oh no,
I've
this
com-
is gives you 1 1, right?
this one. 1 goes to 2.
And
2
then
goes
2
to 1. Oh yeah, right. This is not
Oh,
good.
okay.
So wait,
The
wait.
first way
That's
was
1t.
So-
1. Oh yeah, right. It's 1 goes to 1.
Okay.
2. 1 goes to 2.
Right.
And
Okay.
2 goes to 1 because it also sends 2 to 1.
Yeah.
And 2 go. 1. Sorry.
One.
2 goes to 1 and then 1 goes to 2. So it's 2.
But in the wiring diagram, we read from the top to bottom, right? So I don't really.
Yeah, that's the
get confused.
convention that I use. So I was also
That's just a
confused.
convention, I mean.
Uh-huh.
Yeah, this is a
Okay,
convention. So I know it's confusing because I was also confused when I was preparing this lecture. So forget about it and just stick to this convention. Yeah, that's
Okay,
enough.
alright,
But
alright.
we can make it all correct with
Uh-huh.
this. Yeah. But if you think about the order, it's confusing. So forget about it and just try to use this convention. Okay. And for this, there are so many. So I'm gonna just. By the way, here is a f2 equals 2. 3. So in this case, actually, yeah, S2, S1, S2, T, S2, S1, which is like 1, 2, 3, S1, S2, T, so it's merged like that, like this. So it's actually 1, 1, 3, 2. So 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 3, 3, 1, 3, 1, 3, 1, 3, 3. Right? So the length of this has a length, how many? 1, 2, 3, 4, 5, 6. And it turns out that this is a unique, this is the only longest element for in this case. So up to this point, you may guess, oh, there will be a unique longest element. Yeah, that's not true. N equals 4. Oh yeah, here I draw. Yeah, this is N equals 4 case. Oh, by the way, I gave 2. They are the same. You know, these W's are the same, but I drew a different way to merge. So the different merging sequences, right? I merged 4 first and then 3 later, and then here I merged 3 and 4. But if you count the number of mergings and number of crossings, then this is actually 12. This is 11. So this is bad. This is not the right way because because the length is the minimum number of generators needed. So this is actually the right reduced work. So in this case, this is longest element in this case, but this is not the only one. So in this case, n equals 4. F11 is 11. Right. F4 is 11, like this. But there are 5 longest elements. 5 the longest elements. Like 1, 4, 4, 4, 2, 1, 4, 4, 3, 4, 4, 1. That's over there. 4, 3, 3, 4, 3, 4, 3, 4. So these are 5 elements that have length 11. So it's not really clear what the longest elements are. So the problem, obvious problem, is that first, characterize longest elements in Fn and find the length. So these are the questions that we were interested in, yes and I.
Excuse me? What's the length of 4444?
4444.
Yes.
I don't know, but we have to write down the
Just
yeah.
merge
But it's a-
everything to 1.
yeah.
You have to first put the 4 in.
For
Yeah,
merge
right.
everything to the last one. It's
Yeah.
different than merging everything by first one.
You bring 4 from the beginning and then do
So
this.
that seems
So
intuitive.
good exercise. And all I can say right now is less than 11.
Okay.
Bring 4 to the beginning, and then you only have to bring 3 to the. There's
You make something 4 and then you have to put it away, get something else. And do 4.
Yeah, right.
Once you get 4 in the first place, then you only have to go to the second.
So this
I think
n equals 4, you enumerated everything and
Go to
just
the first.
Yeah.
Okay.
By computer.
Just
we
brute
gener-
force.
Yeah, brute force by computer. So. Any question so far?
So do you have any stability?
Any what?
Stability.
Stability.
So what I mean is if the number of the length is opposed to the n choose 2,
Yeah.
roughly if we have some permutation whose length is roughly n choose 2 minus t, then can we modify small number of the
everything to the
things
left
to make
should
it
be
to
less,
the
more than everything to the first.
Mm, yeah, we haven't tried that way. By the way, this is like work in progress. We still there are many things that still need to be filled in. So that's why I'm hoping that some of you can help us. Yeah. So we don't know much right now.
Can't you just do like
You
this
choose some
and then
other
these
key.
bounces and this?
Right, yeah, that's another question that you can ask,
Oh,
but
that's
we
right.
haven't tried. So we only take this key.
That was I was.
Of course, you can choose other T, and there will be something else, yeah. But or could be equivalent in some sense, but we haven't tried that much yet.
What was the question? Stability?
Or different generator.
Just for the
For
the
the
original.
people are complaining about the stability things. So my question is, when we are concerning about the original program on the permutation, if some permutation has length roughly almost same as n choose 2, then can we just swapping small number of the element to make it to the extremely exact order?
Okay, I see.
That's why I use the term stability.
In the permutation, isn't everything very easy to understand? You just count how many transpositions.
Yeah, I'm not entirely sure I understood your question, but I think what I'm going to tell you from now might be related to what you are asking.
It's almost true by definition.
All right, now let me tell you some of our main result. So 3. Was there 2? Yeah, I used 3 in my note. Oh no, 2 actually. Main result. So first we need to define something. So let sigma is as a word or as a function. Let's fix sigma. Oh yeah, and I'm gonna say an integer I, a singleton of a sigma if I appears only once.
You mean sigma I?
In sigma, no, just I, integer I. In appear in I, like 1.
Oh, okay.
And I is a doubleton if it appears twice, exactly twice. Like this, the 3 is a doubleton. And I'm gonna, because working with this entire function, the set of all functions would be maybe too complicated, so we decided maybe we can focus on this AN, where the set of all functions, this has only singletons and doubletons. That means every number appears once or twice, or 0, it does not appear. And Bn, only, not this, doubleton only, Bn. So n must be integer, even integer. And so An, Bn will be defined the same way. An length of the functions that have only doubletons and singletons, and Bn, okay? And our conjecture is for n greater than or equal to 3, so actually the maximum length can be obtained using this singleton doubleton stuff. the conjectures are checked up to 9. N equals 9, we check this by computer.
So Fn is the notation.
Oh yeah, right. Fn is
Oh, it's written.
yeah,
over
yeah.
there.
Like, capital F or script F.
Well, what does this mean, this X and B?
As
No single.
no singletons,
Okay.
doubletons only doubletons. Yeah. Okay. Because of this, just assuming the conjecture, we can just focus on A, right? Because conjecturally, that's we have some reasons to believe why this is true. Except just for apart from this, we have some idea, but it's we don't have a complete proof, so it's a conjecture.
But do you know that Bn is less than An?
Yeah, Bn is less, right? Yeah.
Why do you only write up to n, like sigma once up to sigma n? Are those like function compositions or
Oh, these are words. These are words.
like?
Like actually, this is actually correct way is this.
Ah.
Yeah, I'm because I'm like identifying functions with words like this.
Mm.
Yeah, this is the same. They mean the same really.
A good question.
Yeah, yeah.
I also thought like
Well, it's not a composition. Yeah, it's just the words. About W1, W2, W. Okay, and one thing that you want to notice here is that although this seems true, it doesn't mean that every longest element can be obtained from this. Because look at this, 1, 4, 4, 4. There's a longest element, but it's not in A, because 4 appears 3 times. But if you look at this one, then it is in A. So for some element in AN, it has the maximum length. That's the conjecture. All right, and we have a lemma. So assuming this conjecture, it is enough to understand AN. Okay, and in fact, AN and BN are quite closely related. Maximum S choose 2, 2S n minus S plus B S n minus S. So in other words, if you understand BN well enough, then you can understand AN relatively easily. So from now on, we're gonna focus on BN. Okay? That's what we want to do now. Yeah.
But do you know the length of when you send everything to a single element?
Like K.
Yeah.
Oh yeah, I
Have you
think
computed those
that
lengths?
should be easy.
Uh-huh.
Yeah. That's not going to be too hard. I think.
Okay. And they are far from the maximum.
I think so, yeah.
Do you have some candidates among the elements in AN which obtain the maximum?
No, we don't. We don't really see patterns because here already there are five longest elements, and increases the number of longest elements increases quite. There are many more, so we couldn't find any patterns there yet. So
I have a question related to this question. Is there any longest element which does not contain n?
does not contain n.
So
Oh, good
the
question.
case of n equals 4,
Ah.
every element contains 4. So I wonder whether there is another example. which
I
is
see. Maybe that's another conjecture then.
Okay,
An's conjecture. Yeah, conjecture. An. Oh, AN. AN in AN. N must be.
And in AN.
Okay, I'm not gonna write that down, but I think everyone understood. Yeah. So there are many things that we don't know. Yeah. So.
Did you guys try putting in any of the sequence A N, B N, or F N into the online encyclopedia of integers?
Yes, we did. No matches.
No match.
Yeah. All right. Now we are gonna focus on Bn, and now let me erase this.
Do you have some general order one?
general upper bound, like yeah, right. We have some upper bound for B. Yeah, so for B. So that's what we are going to do. So we want to find upper and lower bounds for Bn, asymptotically when n increases. And there is something, that's when this Slater indices come into play. That's the interesting part, I think, for people here, I guess. Yeah, so we're gonna use this concept, merging sequences. Oh, by the way, I'm gonna introduce this notion. A two-word is just is of length n, length 2n. Is just a permutation of n plus 1, n plus 1. So every n plus 2, n plus 2, so 2n, 2n. So from n plus 1 to 2n, they all appear twice. They're multiset. So we'll rearrange them, and that's a two-word. Okay? And W2n is going to be a set of all two words of length 2n. And this is a subset, or maybe strict of Bn. Because this is a permutation, which is a word, is a function, right? And every number appears twice as a doubleton, so it's in Bn. And in fact, this is something that can be proved easily. B2n is, we need to only look at this. Or maybe this is related to Ans's conjecture. Yeah, maybe the Ans's conjecture is proved. We only need to look at these. Yeah. We only need to look at the words that has like maximum numbers, yeah. Largest numbers. Okay. Because here you see like 1, 1 is less than 2, 2 in terms of length. So if you have like bigger numbers, the chances are higher for being length being bigger. And now, let's say D is a wiring diagram of say reduced expression. So we have these two words, and then consider a wiring diagram. Okay. Let's just forget about this reduced expression. Any expression, and then think about the wiring diagram. Okay. And we have to merge like n times because n doubletons. And the merging sequence of this wiring diagram is just a permutation pi 1 ... Let's say there are always n merges, where pi I is the integer merged at ith merging step. Let me explain this using a diagram.
Is it clear that a reduced sequence that there always exists a reduced sequence with the minimum number of merges?
The number of mergings is always always n.
It's not like here, this one here, there's 2 merges, but there's only one.
Oh, yeah, right, because it's not reduced. That's right, yeah.
This one is reduced. This is reduced. This is reduced, isn't
Really?
it?
How do you
Yeah,
know
may-
it's reduced?
It's
Yeah, right.
1, 2, 3, 4, 5, 6, 7. Because you could get. I mean, you could get the
How do
same
you prove
length.
something is reduced?
Yeah, I think this is reduced.
Okay, I think for any expression, this makes sense, right? And let's say it's k. If there are
Yeah.
k merging
Okay,
sequences,
then-
Now
okay.
it makes sense.
Okay, yeah, now it makes sense. Yes, right. Let me give you an example that I drew over here. Yeah, so this is the merging sequence. So this is pi 1 is 4, pi 2 is 3. So here pi 1 equals 3, pi 2. So our merging sequence for this wiring diagram is 4, 3. and this is a 3, 4. Okay. And you can notice here, once you fix your merging sequence, actually this is the best. You cannot do better than this. And if you fix this merging sequence, actually this is the best. And that means this merging sequence is more efficient than this merging sequence. And I'm gonna show you.
What do you mean? What the best?
I mean minimize the length, because we want to minimize the length. This is bigger. The number of crossings is bigger than this. So yeah. We want to minimize this.
So what is best, to merge in the order like 3 comes before 4? No, what was
Oh.
best? I don't understand what you mean. What is best?
I mean,
just in this
for
picture.
in this
Oh,
in this
okay,
case,
okay.
yes. And yeah, that's something that's related to what I'm going to say. So you can get some idea here that maybe the merging sequence is important. But we found a theorem or proposition. Now let me state or lemma. So D is a wiring diagram. Let me just say wiring diagram of W, meaning the wiring diagram of any expression of W. So just fix this wiring diagram. Oh, actually no. With a merging sequence is fixed, and also with a minimum smallest length. Fix this and then consider the wiring diagram with the smallest possible number of mergings plus crossings. Okay, just like that. Then we have the number of mergings plus number of crossings in D can be written in this way. 2n squared plus n choose 2 crossing. I'm going to explain what this means. Crossing pi inverse or reverse w. Okay, so what does this mean? So pi is a merging sequence n plus 1 and 2n. So everything must appear like once here. So it's a pi 1, pi 2, pi n. So we connect them, and then when you connect them, there will be crossings. So we want to minimize number of crossing by this configuration. So it's the minimum number of crossing. That's what this means. Crossing. You connect them with minimum number of crossings. That's the statistic for this. And what is cross this? So this means pi n. I'm going to reverse the word pi. That's why it's pi reversed. I write pi in the reverse order. And here it's going to be w. So here we have only n in numbers. Here we have 2n numbers. So everything, because this is a doubleton, it has 2 strings attached to it. 2 strings attached. So everything locally looks like this. And you connect them. Like this is A, then you find 2 A's over there, you connect them. Something like that. And then you find the number of crossings there. That's what this crossing pi means. Okay? Let me
So these crossing numbers is super easy to read off just from the permutation, right? And
yes, this is actually what's called inversion,
Yeah,
double
yeah,
inversions.
right,
Yes. Yeah, this is easy. This is also quite very easy.
Yeah.
So let me give you an example with this. So here, this is actually, this is number of mergings plus number of crossings for this particular merging sequence. Because 1, 2 mergings, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 2 plus 9. 2, 3, 4, 5, 6, 7, 8.
You didn't count one. There was one more.
Ah, yeah. right. Thank you. So let's compare this with that lemma. So pi equals 4, 3. So what is pi crossing? So 3, 4, and here you write 5. So you have to connect like this. So the crossing of pi is 1. And what about yeah, enough space. So here across of pi w is 3441 443. So pi we have to reverse, so it's 3 and 4, right? And 3, 4, 4, 3, and then you connect like this. And there are 2 crossings, so this is 2. So if you plug those in here, then you can see that this is 12. And also this, you can do some exercise, that also gives you 11. So that's what this lemma is saying. So in some sense, the merging sequence determines the length. I mean, the number of crossings, minimum number of crossings for your wiring diagram. That means if you want to really find the length of this, you consider all permutations of the merging sequences, and then you find the minimum of this. Then you can get the length of this W. Okay.
What was two? What is this two word? I forgot.
2 word is like there's a permutation
there
of
it's
these.
written.
Permutation
Oh,
of
it's when
this.
you shift over.
Yeah,
Okay,
yeah,
I see,
yeah.
I see.
Now finally I can tell you something about Slater indices. Yes, final section, connection with Slater indices. So a tournament is an orientation of the complete graph Kn. That means, so, okay, K5, let's say. Let's use K2, sorry, K4. So K4 is this graph. Orientation means for every edge you put a direction. So like any way you want. So maybe this. So this is a tournament. So there are 2 to the n choose 2 tournaments of size n. And we say that a tournament, let's say tournament T is transitive, or also called acyclic, if no cycle. That's what acyclic means, right? This is this transitive?
1, 3, 4.
1, 3, 4. So there's cycles, it's not a transitive tournament. And the Slater index of T, which I'm gonna denote by Slater index of T, is minimum number of arrows reversed to make T transitive. If there are already no cycles, then this is 0. But there are some cycles, you have to reverse some arrows to get a transitive tournament. So the minimum number is the Slater index. This is actually, maybe just one example. Let's say T equals 1, 3, 2. What is the Slater index?
1.
Yeah, you only need to just reverse 1, maybe any of these. If you reverse this, then it's no cycle, so it's 1. And this is actually quite a well-studied object. I mean, by the way, a Slater index of T, if there are n vertices, this is actually quite easy to prove. Okay, this is very easy. This is also easy. I mean, more difficult than this. And this is fairly well studied, dated back to Elvish and Moon, like 60 years ago. And they show that this can increase almost up to this. So there exists, for any epsilon, there exists a t of size n, for large n, such that Slater index is almost that. We can reach almost to this maximum possible.
So it's a random tournament.
Oh yeah, they proved this using probabilistic method. So yeah, the random maybe tournament could. What does that mean? Random tournament satisfies it? I don't know. About this.
But they don't actually construct it. That's the point.
Right, that's right. Yeah. Actually, the proof is quite easy. Just 1 or 2 pages. And Spencer and De La Vega, they showed that for large n, there exists a t tournament such that this is there exists t. This is really the right term, like c1 n to the 3 over 2. Oh yeah, 1 over 2. So it's almost like this for some constants. This is the right order with the right constant factor 1 over 2. All right. Now I'm running out of time, so I'm not gonna explain the details, but let me give you the idea. So we know this. Oh, by the way, I forgot to mention. Actually, this is equivalent to saying that this is equal to 3n squared minus n plus crossing. Now we don't have to reverse. Yeah, these two are the same. That's easy to check that they are the same. So what do we want to do? We want to minimize this, right? Because this is fixed. We want to find pi so that this is minimum possible. That's what we want to do. So instead of looking at the whole diagram, I'm gonna focus on. Okay. Let's just look at just 2 numbers, AB. So AB will appear like AB or AABB, etc. Right? So W has AB, something like that. This is what my convention. So let's just focus on, restrict ourselves to A's and B's in W. And here, so we assume that A is smaller than B. So so this is actually merging sequence. We merge A first and then B later, and then we have to connect them like this. And in the formula at the bottom, we want to compute crossing over here minus crossing over here. So that means this in total, this will give us number 1. Give us number 1. What about this? Number of crossings 1, 2, 3. This is 1. 3 minus 1 is 2. Right? That's what it means. That means if we choose the merging order like this, then we will get 1. If we choose merging order like this, then we will get 2. Right? That means locally this is better. Right? And consider all these cases, like I draw this. I didn't have time to want to. I had to draw like 12 things like this. But the interesting thing is that, maybe here if you compute this, this is 2 and 1. Maybe I'll have to draw at least one more, just to compare. But some other things like AB, like a PABA. If you look at this case, then if you connect like this, then or BA, BA, AB. So let's compute. 1, 2, 3. 3 minus 0, so it's a 3. 1 minus 1 is a 0. So the idea is, if this kind of pattern appears, then maybe if you can choose carefully, then we can choose this. I mean, just think about it, that situation. That means this has more chances to minimize the length. So maybe if you have only configurations like this, at least we have 1. But in this case, we may have just 0. And there are actually one more pattern here. So this is ABAB, BABA, and ABBA also has this kind of situation, 2 and 1. And what I'm going to do now is I only consider those 2 words having only these 3 patterns, not this pattern and other 3 that has like 3, 1, or the other like 4 and minus 1 is even worse, and 0, 3. Because in this case, maybe we cannot really increase, or we have to increase, or things like that. So let's just focus on only this. Okay? And then that's now I can tell you the connection with Slater index. So now a simple 2-word means only like those ABAB, BAAB, ABB, A patterns, where A is always less than B. We restrict ourselves to those simple words, okay? And W prime will be simple words. Okay? Of course, we restricted ourselves a little bit, so we may get something not the best, but this is still quite
So it
good.
means for every
Every
I
AB,
and
every
J.
AB, every AB. Yeah. And I'm gonna define a tournament using from a simple word. So definition. W is a simple 2 words, and in W2n, I say it's prime. So T of W is a tournament on n plus 1 dot 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 2n. So all we have to do is to decide the direction. So A to B if the pattern here is ABAB. And if and only if. If and only if. So we define this. So let me give you an example just to make sure that yes, you can understand this. W 5 4 6 4 6 4 5. Then what is the tournament? So we have 5 4 6. So for 5 4 4 is smaller. Look at 5 4 and 5 4 4 5. It's not like 5 4 5 4. That means direction goes like that.
I see.
And 4
So that's A smaller than B?
So
always A smaller than B. And 4 6 4 6 4 6. That means the direction is the one. And 5 6 6 5 is not 5 6 5 6, so it goes to this. The tournament looks like this. And the theorem is that in this case, the length in this case the length is this is 3n squared minus n plus n choose 2 plus the Slater index of T of W. The reason behind this is that the way we construct this tournament is that we selected so that we get the minimum ones, like 1 1 1 1 1. So if you change the direction, that will give you 2. So whenever you change the direction, you get extra 1. That's why the tournament appears here. It's like a very simple explanation, but the idea is that. And from this, because we know this is actually now corollary is that.
But can any tournament give you the corresponding tour, simple tour?
Simple tool?
I mean, so
Every tour gives you a tournament, but does it go the other way?
the other way.
No.
No. Okay.
Yeah, that's the difficulty. But we were able to do something. So the corollary is that for large and even integer n, capital N, the Bn, the maximum length for 2 words, this is less than or equal to I didn't cancel this. This actually follows from this trivial bound of the tournament, like from 0 to 1/2 and choose 2. So I just use the trivial bound. So that gives us this. But we were able to construct some what's called regular tournaments. Then from there we were able to show that we can improve this like that. But if you can find a tournament that gets the maximum number, the maximum Slater index, then this becomes this. So the conjecture is, or maybe hope, is that this is really this. And to do this, it's enough to construct, enough to find tournament T from, okay, maybe I should write it this way. 2 words such that the tournament of the Slater index of this is 1/2 and choose 2. It's like the maximum index, Slater index. We were able to find the tournament with 4, 1/4. That's why we got this. But if you can find this, the maximum, then yeah, I think this is true because we don't have to get the exact number, exact Slater index. We have some asymptotic anyway, so maybe these 2 words there are enough 2 words to construct tournaments with a big
Like a random
Slater
tool.
index.
Yeah.
Yeah,
Or like,
right.
I mean, what is the probability that random tournaments is realized?
Yeah, that's right. So that's something that I don't know. That's why I'm looking for your help. So that's all I wanted to say. Thank you for your attention.
Thank you. Oh yeah. Questions? Yeah.
In the case of Sn, if you try to draw a wire diagram, then you just place the elements in 2 lines and just connect them in the line, then
Yeah.
somehow make it to, then you get the minimum number of crossings. Is there an somewhat natural way to draw this case on a plane with some fixed rule to obtain the minimum crossing?
You mean this?
Yeah. For example, if you start from A, B and try to go to A, B, then each part would be consisting of 3 line segments.
Yeah, right. Yeah, we try to investigate those, and then we even call them like Y diagrams. But we don't get much from there. Yeah, we didn't get much.
So slightly related to this question, but in the case of Sn, I mean, important part of that is these Coxeter relations.
Right.
Do you have something similar in this?
We haven't.
I think all reduced words in Sn will be are equivalent via the braid relations.
Yes.
Do you have some similar thing like braid relations here?
Yeah, we haven't thought much about it, but maybe this could be related to what you want to do. I mean, eventually, because we want to minimize the number of crossings. For Sn case, the fact is you cannot have 2 wires crossing more than once. If you don't have situations like this, then that is reduced. That can be shown. But for wiring diagram for Fn, then there could be more. Obviously, this way, this already has crossings like this. But somehow we can understand once we fix this merging sequence, and that's how we got this. So once you fix the merging sequence, then we can understand the crossings quite well. But the problem is there are many merging sequences, then we don't know how they can be minimized.
Seems like that probably give us some bound for the number of longest elements in Bn. Is there a better bound?
You mean this?
I mean, I wonder the number of longest elements in Bn.
In Bn.
Is there any bound?
Number of longest.
Oh, number of longest elements. No, we haven't thought about that. Yeah. But right, we also computed the number of longest elements, but that we couldn't get any patterns there. So,
I was thinking, you fix a function and the number of reduced words or representations.
yeah.
Did you? look
Oh
at these
yeah,
things?
that's
I mean, that's classic.
Yeah,
in
right,
the
that's right.
Symmetric group.
right. I think even for the symmetry case, that's known, but it is less easy.
Uh-huh.
So yeah, I think even for this case, it's be
Mm-hmm.
more difficult than what we have been doing.
Mhm.
Yeah.
Do you have something about the average length?
Average length.
Yeah, can you
Oh.
instead of maximum length,
I
what's
see.
the average length of the all toward all
I see.
all Bn?
Right, but we
Yeah.
haven't tried. But I think that's a good thing to try.
Some simple upper
Yeah,
bound.
yeah. We haven't tried yet.
Have you ever imagined something like falling of like permutation in the case of symmetric group and
Ah. No, we haven't, but it will be really nice if there's such a thing.
All right. Okay. Let's thank the speaker.